Second question. Explain how you distinguish between each of the pairs of compounds using each of our spectroscopic methods. First compound. Well, with any of them, my place to start with this is just to go through and get an idea of what precisely you would be looking for each molecule in terms of number of signals and splitting and integration and all that. So I like to set out kind of a chart layout of this. I'm not sure precisely how much space you had for this question on the exam, but if you don't get a lot of space, practice writing small. So, this guy here, we've got a little bit of symmetry going on right here, where these two methyl groups are going to be the same thing. So, that's going to give us one signal that integrates to 6, and as a splitting of a singlet. No hydrogens here. We got 2 hydrogens here. They are going to be coupling to this CH3 over here, which means they're going to be a quartet. So integration of 2 as a quartet. And of course, this methyl group over here, integration of 3 with a splitting of a triplet. And I presume at this point that you know where I'm getting these splitting values from. Neighbors plus 1 and all that. We can talk about the OH if you want to. Notice that between the two compounds they both have an OH, so that's really not going to be any different. And we're not talking, he doesn't tell you whether we're doing this in a protonated solvent or not. So you have enough data, I think, without the OH to try and tell the difference between these two, because the OH is perhaps not going to be as much help as it might. Moving into CNMR. Again, these two methyl groups are going to be the same thing. And this guy's going to be his own thing, this guy's going to be his own thing, this guy's going to be his own thing. So that means that we have 4 different signals here. You can get into where precisely they're going to show up, but that level of fine-tuning is not overly important here, as we'll see. So, we're going to say we have got 4 signals. IR, we've got an OH. That's really all we can tell, that's really all we care about right now. So, second molecule here. We have a plane of symmetry throughout the entire molecule, rather than just a localized symmetry like we had up in the first one. Which means we only need to look on the plane of symmetry into one side of it. We've got a CH3 here, 2 H's here, and an H sticking off here. That's going to give us 3 total signals, like we had for the other one, but perhaps they're going to be a bit different. So, starting with this guy here, he is going to have an integration of 1, and he is going to be not a triplet, he's going to be a quintet, because he does have a total of 4 neighbors. They're all the same, so they wouldn't couple to each other, but they are going to couple to him. These guys, 2 hydrogens. Don't be tempted to say that this is going to have an integration of 2, because remember our plane of symmetry. These guys are going to have an integration of 4. And what is their coupling? Well, let's just say that this neighbor is going to be about the same as this neighbor, and you can say that maybe they'll be a quintet. Or, if you want to be a little bit more specific, they are going to be a doublet of a quartet. And our methyl group, again, not going to be an integration of 3, it's going to be an integration of 6 because of our plane of symmetry. And what is he going to show up as? Is he going to show up also as a quintet? No, because each individual methyl group is only seeing 2 hydrogens. He's going to show up as a triplet. CNMR, plane of symmetry, we have 1, 2, 3 types of carbons. 3 signals. And for our IR, we also have that OH, and again, there's really nothing else interesting about all this. So, what are our major differences? IR, don't got much. So, no real difference between IR, and you can say that using IR, it's not going to be extraordinarily easy to distinguish these two. You'll see if you go on to other levels of chemistry that there is ways to tell these apart, but it's all, most of it down in the fingerprint region. So, CNMR. This is a fairly distinct difference here. We got 4 signals versus 3 signals. Just write that down. That should be good enough. HNMR. Personally, I would just write all of this stuff down, that for this guy you'd expect these, and for this you'd expect this. If you want to pull out individual signals, you can say that you're going to have this guy, very distinctly, integration of 1 is a quintet. You don't have anything in this molecule that is going to show up as an individual hydrogen. Otherwise, integration of 6 is a triplet, yeah, no. It just I would write down all of this personally. So, next molecule. Or pair of molecules, I should say. We've got 2 substituted cyclohexanes. We've got a 1,1,4 dimethylchloral cyclohexane. And don't quit on that name, I'm just making things up. Okay, and a 1,3. So, what do you notice right off about these guys? What's going to be our major difference here? Major difference is going to be that this guy has a plane of symmetry, and this guy has no plane of symmetry. So, which one would you expect to have fewer signals? This guy, plane of symmetry. No plane of symmetry equals beaucoup signals. So, HNMR, we've got our methyl groups here, which are going to be singlets, because they're not talking to anybody. And next over, we've got 2 hydrogens here that are going to be triplets, because they're only talking to these 2 hydrogens here. And then we've got another 2 hydrogens, which are also going to be a triplet. Now, if you are very familiar with the way HNMR works, you should be thinking to yourself right now that these hydrogens are going to be further downfield, meaning bigger number, than these 2 hydrogens here. You can put that if you want. And then finally, we have our hydrogen here, who's going to be in the furthest downfield of the block, and he's going to show up as a triplet. Okay, CNMR. Count everything on the plane and to one side of it. So these 2 methyl groups are technically on the plane. And depending on how picky you want to get, you can count them individually. And you could technically have counted them individually for the HNMR as well. What's going to make them different or the same is going to come down to how fast this chair is interconverting between its 2 chair conformations. Because if it's not interconverting at all, you're going to see one of these methyl groups show up as permanently axial and the other one show up as permanently equatorial. If it's rapidly flipping between the 2 chairs, they're going to equalize and show up as about the same. So you can write that down if you want. I'm sure that he's going to be impressed if you write all that down, but then again realize that they don't really like to read long novels. So, depending on how you want to count it, we can say that these 2 are the same, because we did that for the HNMR, so let's just be consistent. So you got 1 signal, 2 signals, 3, 4, 5. 5 total signals. IR. Well, there's nothing here that I would really pick out. Nothing here that strikes me as being very strongly different. Honestly, it's only the last pair of molecules that's going to have a big difference in the IR. Let's see what he says. Nope, he doesn't have anything about IR either, so don't worry about it. Okay, get down here. So, got no symmetry. For the sake of simplicity and getting a fairly fast answer here, let us Again, say that these this cyclohexane is going to be rapidly interinverting between its chair conformers, which means that we can count these two methyl groups as being identical, or closely enough identical that we don't have to worry about them being terribly different. Again, if you want to put in the fact that if one chair is favored over the other, and if you want to be terribly all for it, you can actually go draw the chair conformers and figure out if one chair is going to be preferred over the other chair. Hint, it is. But for the sake of simplicity, let's just say that they're going to be identical. So methyl groups can have an integration of 6 again, and they're still going to be a singlet. So that's not going to help us tell these two apart. Got 2 hydrogens here, and they are talking to 1 hydrogen. So integration of 2, that is going to be a doublet. Oh, sorry, I've forgotten. These guys up here are not going to be a triplet. They are going to be a doublet of a triplet, or if you want, a quartet. That's my bad. Okay, so moving on, this guy here is going to be our farthest downfield hydrogen. Integration of 1, and he is going to be a quintet. These guys here, integration of 2. They are going to be, again, doublet of a triplet. Moving on, these guys, you can count it as a triplet of a triplet, or you can count it as a quintet. Functionally, it's going to look most like a quintet. It's not going to be exactly a quintet because they are slightly different. Well, okay. I'll get into that a little bit later. So, these guys have an integration of 2, and they're going to be a quintet. These guys here, again, integration of 2, and they're going to be a triplet. So, you'll notice what I mentioned before, that this has fewer signals and this has a lot more because of the lack of symmetry. Realize that these are chairs, and because you do have distinctions between the axial and equatorial positions, it's not going to be anything like as nice and neat as I've laid it out here with doublets and triplets and whatnot. Most likely, this is going to show up as a huge mess. So, if we're being completely honest here, this is going to show up as an absolutely huge mess, and this is going to show up as a lesser mess, but they're both going to be a little bit messy. So, CNMR, again, no symmetry. We're going to count for right now these two methyls as being equivalent. So you have 1, 2, 3, 4, 5, 6, 7 types of signals. This question is perhaps, I don't know, this particular pair of molecules gets a little bit complicated in terms of telling them apart. Your best bet for these is going to be your CNMR, because your HNMR is going to be a mess either way. Just as a hint for if you have to solve something for lab or whatnot, and you see an absolute mess in the HNMR, most likely it's probably going to be a cyclohexane of some sort. Okay, third pair of structures. And you will notice that these pairs of structures are essentially identical to our first pair of structures. And you can't even see half that molecule, I apologize. Okay. So you'll notice that they have exactly the same base carbon skeleton as our first pair of molecules. We've just thrown a bit of a wrench in here by putting in our deuteriums. What does this mean? Well, it does actually mean quite a lot, because what we have done is tossed in stereochemistry where we did not have any before. Also, important point, deuteriums don't show up at an H NMR. They are still H's, but they're not magnetic in the same way, so we don't need to worry about them at all. Which, to some extent, simplifies things. So, we have stereochemistry. Where's our stereocenter? This molecule, where it's the only carbon that has 4 different things, it's going to be this guy here. He doesn't have an H. So you should be thinking, well, why on earth does this matter? It matters because of our enantiotopic diastereotopic stuff. By having a stereocenter in this molecule, we have induced these 2 hydrogens to stop being enantiotopic, which they were in the previous pair, just be diastereotopic. Because that's essentially how you tell if something is diastereotopic. If 2 essentially identical hydrogens are on a molecule that has a stereocenter anywhere, preferably closer, because the closer it is, the bigger difference you're going to get, they become diastereotopic. And we'll get more into that later when we get to the problem where he actually asks us about diastereotopic and antiotopic stuff. So, these 2 hydrogens here, instead of showing up as a single signal, are going to show up as 2 different signals, and they're going to couple to each other. Let's start in the same place we did for the first molecule, though. Let's start with this methyl group here. He's going to have an integration of 3, and he's going to be a singlet, because he's still really not talking to anybody. Okay, now we move over to our diastereotopic pair. They're going to be relatively close to each other, but they're definitely not going to be the same signal. So each one is going to have an integration of 1, and each one is going to be a doublet of a quartet. This is one that you can absolutely not simplify down to say that it's going to be a quintet, it's got 4 neighbors. Because the coupling to a diastereotopic proton is huge. It's extraordinarily large. It's one of the largest couplings you will see. And so therefore it's going to be very different from any other couplings you'll have, and they're not going to kind of blend together. So each of these guys is going to be a doublet of a quartet. And our CH3 on the end, he's going to have an integration of 3, and he is going to be a doublet of a doublet. Again, his coupling to each of these things is not going to be the same. So they show up as very different protons. They have very different coupling constants. So he has to be a doublet of doublet. You cannot simplify him down to a triplet. Realize that as you move a doublet of doublets closer to each other, they'll eventually overlap and become a triplet. So if these 2 couple to this methyl group in about the same way, it'll show up as something that looks vaguely like a triplet anyway, but you should be aware that it's not going to be a triplet. Not in reality. Which is another huge discussion, because there's a school of thought that says there is no such thing as triplets anyway, every triplet is just a doublet of doublets. But, simplicity's sake, we like to talk about multiplets. CNMR. Now, in the first pair of molecules, we did have a little bit of localized symmetry where the 2 methyl groups were the same. We don't have that. No symmetry whatsoever, nothing, nada. So, every carbon is different. 1, 2, 3, 4, 5. Our IR, we're going to have an OH peak. And if you want, you can say that we're going to have a single peak representing this CH coupling. Sorry, CD coupling. Second molecule here. If you'll recall, our first pair of molecules, the analog of this guy had a plane of symmetry, and he was fairly simple to categorize. This guy, no symmetry. Also, this guy has a stereocenter. Where's that stereocenter? Right here. Which means what are we going to have? Diastereotopic hydrogens. Which ones are going to be diastereotopic? These guys. Okay. So, starting from the outside edges and working in, we've got this methyl group and this methyl group. They're each going to have an integration of 3. They're not the same thing because we don't have any symmetry anymore. He is going to show up as a singlet. He is going to show up, like our guy up here, as a doublet of doublets. Deuteriums don't show up, so let me just worry about our diastereotopic guys. as before, they're each going to show up with an integration of 1, and as before, they're going to show up as a doublet of a quartet. Guy in the center is a D, and so we don't have a signal for him. So that's it. Ta-da! Ends up being actually just about as simple as it was before. So, moving on to our C NMR. Again, no symmetry, everything is different. 1, 2, 3, 4, 5. And he's going to have an OH peak in the IR, and if you want to get kind of splitting hairs, I would say that there is going to be 2 or 3 different CD stretches here. I don't know enough to tell you if that's going to be something that's going to be readily obvious for this. So, me personally, not knowing if this is going to be a significant of enough difference, I would not put it on an exam. Let's see if he mentioned it at all. And he doesn't say anything. His comments are mostly about the mass spec of this. Which, I suppose he did mention mass spec for all of these guys, and I don't know, my forte is not the mass spec, and I hadn't been thinking about it the whole time, so maybe I'll go back and, for each of these guys, make a comment on that. But for these 3 types of spectroscopy methods for this pair of molecules, HNMR is going to be your biggest assist here. But, as you can see, it's not that much of an assist, because each of them has 2 signals with an integration of 1 that are a doublet of quartet, and they each have 2 signals with an integration of 3, 1 is a singlet, 1 is a doublet or doublet. So that's not going to help you terribly much. That's why his answer for this one is relying entirely upon mass spectrometry. If you want to know what he's talking about, is mostly how easily things get knocked off. And I believe what he's saying is that the OH have differing levels of how easily they are knocked off. This OH is on a tertiary center, which means that it's fairly okay for him to leave, it's fairly stable for him to leave. This guy is on a secondary carbon, and so it's not going to leave as readily. So you're going to see the fragment representing this chunk of it a lot more prominently for this guy than you would see it for this one. Okay. Final structure, pair of aromatic rings. Aromatic rings are always fun. And this guy is where our IR, which is apparently one of the hardest sentences in the universe to say, is going to come into play. Because you should notice right off that there is a major difference between these two in terms of our most prominent IR signal. And what is that? That is, of course, the OH. This is going to be your biggest distinguisher between these guys. So, he's going to have an OH, and he is going to have no OH. Right off the bat. And in terms of strategies for taking exams, it's a particularly good idea that if something is very easy and right there and whatnot, write it down. Because if the other stuff is a little bit more complicated or takes longer or whatnot, you don't want to chance that you'll forget to write down the easy thing or run out of time to write down the easy thing, and therefore lose points. So, H&MR, we've got a tri-substituted benzene here, which is going to have 3 signals in the aromatic region, which is the 7, 8. This guy is only di-substituted, which means that he is going to have 4 signals in the 7, 8 region. I apologize, my format has apparently changed. Meh. And then this guy is going to show up essentially the same for both of them. CNMR, we're looking at the same sort of thing. That we have 1, 2, 3, well, okay. In either case, we've got a lack of symmetry here. So 1, 2, 3, 4, 5, 6, 7 signals, and 6 of them are going to be aromatic, which is the 120 region, and one of them is going to be a ketone, which is going to be up about 200. This guy, exactly the same thing. We still have 7 signals, and 6 of them are aromatic, and one of them is in this case, he's not going to be a ketone. He's going to be an ester, which pulls him down a little bit. He's going to be down closer 170, 180 region. So, if you want, that's a difference. And I think it's 150 to 180. 190 rather. Okay, so HMR, 3 in the aromatic region versus 4 in the aromatic region. CNMR, our main difference is going to be this ketone versus an ester. And IR is going to be OH versus no OH. So out of all 4 pairs of compounds, this is the easiest one to tell apart. You could look into mass spec, and that's going to be mostly, you're going to have an ion here for the H getting knocked off, or you're going to, and in both cases you'll have the CH3 knocked off. I wouldn't worry about it terribly much. The mass spec was mostly for that third pair of molecules, which were not readily apparent any other way.